Modern commercial buildings across America are unknowingly poisoning their occupants every day, while actively trying to keep them healthy. Current health protocols dictate increasing outdoor air intake to dilute indoor airborne pathogens like COVID-19 and RSV. But this protocol creates a dangerous paradox during acute street-level pollution microevents. Concentrations of PM 2.5, fine particulate matter that easily enters the bloodstream, can vary by 300 to 500% within a single city block. Current building management systems, the computerized networks controlling mechanical operations, have absolutely no real-time data regarding the air outside their own doors. Indoor air quality sensors only trigger alerts after the polluted air has already been ingested into the space. Without an external data layer, indoor air quality is entirely hostage to outdoor data blindness. The reason buildings lack this intelligence comes down to the nation's fragile monitoring infrastructure. The United States relies on roughly 1,400 static EPA stations to cover 3.8 million square miles. A commercial building in a city like New York might be operating its ventilation using data pulled from a station 50 to 100 miles away. This map highlights the spatial discrepancy of using regional data for local decisions. A single city block is completely lost within the 2,700 square mile coverage assigned to one EPA station. Because these stations report 24-hour averages, they are useless for detecting sub-minute localized pollution spikes. Satellite tracking is equally inadequate, as its spatial resolution is limited to multi-kilometer pixels. Effectively managing a real-time HVAC system using static station data is like driving a car while looking at yesterday's regional weather report. The core engineering problem is determining how to map sub-minute air quality across an entire city without the impossible capital expense of installing hardware on every single building. Sparrow Analytics solves this by decoupling the sensors from the buildings and deploying them continuously on existing commercial and postal fleet vehicles. These mobile nodes capture environmental data at a 1 to 5 second temporal resolution, pinned to a 5-foot GPS accuracy. This visualization shows the mobile nodes actively mapping specific parameters, including high-grade electrochemical tracking of nitrogen dioxide and optical particle counting for particulate matter sizes ranging from PM 0.3 to PM 10. A machine learning layer analyzes this continuous mobile coverage to perform source attribution, distinguishing a temporary traffic surge from regional smog. This allows the system to accurately forecast the duration of a localized pollution event down to the minute. To be viable for engineering use, this data must maintain strict scientific rigor and match EPA reference standards. The system's accuracy and statistical significance undergo an independent technical audit by EPFL, a leading technical university. This validation confirms that the network's overlapping mobile hardware redundancy effectively self-calibrates the sensors in real time. The result is a true street-level environmental exposure data layer, available to plug directly into any structure. This established data layer is then routed directly to its operational payload inside the building. Through the Building Intelligence Interface, the outdoor data feed connects directly to the building management system using an API, an application programming interface that allows the discrete software systems to communicate securely. This API connection takes direct control of the physical hardware mounted on the roof. The primary automated action is switching the HVAC system between taking in outdoor air and recirculating existing indoor air. This graphic illustrates a live trigger event. If street-level PM 2.5 crosses 15 micrograms per cubic meter, the interface signals the BACnet system, the standard data communication protocol for building automation, to physically close the intake dampers. Granular data parsing also drives a smart filtration strategy, toggling between MERV13 and HEPA filters, depending on the specific particle bin sizes detected outside. This precise optimization reduces premature filter replacement costs by 20 to 30%. The building evolves from a static shelter into an active, closed-loop machine, responding dynamically to its local atmosphere. The mechanical actions of the 50-building New York City pilot translate directly into measurable epidemiological outcomes. This chart shows the projected Year 2 base case targets derived from preventing bad air ingestion. It illustrates a 60% reduction in bad HVAC decisions, which produces a 35% reduction in indoor PM 2.5 exposure. Using the Wells-Riley equation, a mathematical model used to estimate the probability of airborne pathogen infection, adapted for particulate-bound pathogens, this yields a 30% reduction in modeled transmission risk. The economic return on investment is highly efficient, coming in at a cost of roughly $1.71 per protected occupant hour. Contrast that operational cost against the CDC's estimated $3,800 cost of a single COVID-19 infection. The system achieves a net positive societal return on investment by preventing fewer than 3 infections per building per year. Injecting external software intelligence proves mathematically superior for pathogen control compared to merely upgrading internal fans. The deployment expands rapidly from a 50-building pilot to a multi-year global platform. International expansion targets in 2027 demonstrate that the platform's design is geographically agnostic and ready for diverse urban environments. A fleet-based sensor network relies on nonlinear scaling mechanics. This graph maps that network scalability. Adding a single node to one delivery truck simultaneously upgrades the spatial data resolution for every connected building in the area, driving the marginal cost per building sharply below the $200 a month threshold. This completely eliminates the capital-intensive roadblock of installing and maintaining dedicated monitoring hardware on every individual roof. The future of smart architecture isn't built with better static sensors. It is built by plugging passive structures into a living, real-time atmospheric intelligence matrix.